So this is a work in progress report on a project that Giles and I are working on and a couple of other people. We're looking at statistically solving, because I like alliteration, statistically solving sneezes and sniffles step by step. And so particularly this is a work in progress, right? We haven't solved this problem, but we're giving you an update as to where we are. So who are we? Well, you know that I'm the co-chair for the conference, and I've been an industrial data scientist for 15 years. And my colleague Giles here, Giles is a bioinformatician turned data scientist. Do you want to say any more about C, or should I introduce you any more than that?
That's all good.
Yeah, it's all good. Right, okay. I'm the author of High Performance Python. That'll be one of the books that we're signing this lunchtime. And I'm super excited that a colleague has brought in my Japanese and my Polish translations that turned up a few days ago, apparently. I'm not signing those, but if you happen to be not an English reader, you can get it in Japanese and Polish. So I run Model Insight. My business partner Chris and I here, so we do machine learning consulting. Giles works with us. And our current client is Endava, and they were good enough to be a gold sponsor for us. So please go and speak to the Endava stand and the guys on the stand over in the far corner. They've got USB lights and things to give away. So go and have a chat with them about big scale industrialized data science. That's fine. So my wife sneezes a lot. And I've got a graph in a minute. She sneezes a lot. Could we close the door at the back, please? It's quite noisy out there. Either, do we need to shuffle forwards? Annabelle, could you middle lot shuffle forward a bit? That's all right. We can shuffle in. And there's some room at the front here as well. Let's do the shuffle-roo. It's a bit like the rowing boat song. Just sit there and. Yeah, no, totally. No, it's not. It's not cool. Oh, yeah, just keep coming forwards. Keep coming forward. You come and sit on my shoulders. It'll be fine. There's room there and there's room there. Keep coming in.
Two or three at the front here. They look quite comfortable.
Yeah, three down there. Three down there. Keep coming forward if you want. If you want, okay. Keep coming. Yeah, please come forward. There's still more coming in. So you at the back, please come to the front. Let's make it easy. Good grief. We might have to sellotape the door shut in a minute. Keep coming forward. Keep coming forward. Well, man, yeah. Right, we did run a survey to see which talks were most popular, and this one and the one in the other room vied for equal popularity, so I chose to stay in this room. But that one's pretty popular too. Yeah, well, it sucks being a popular conference, but thank you for bearing with us. So, my wife sneezes a lot. I've got a graph in a minute to show you how much she sneezes. She's also an iOS developer, so she develops iPhone apps. And we asked the question, so she's been sneezing for 20 years. We asked the question a couple of years ago, hey, couldn't we use machine learning and some clever data science to try to understand the root factors behind the sneezing? So what drives the allergy? So that's the top line goal, solve my wife sneezes, so one person sneezes. But the more general goal is, could we reduce symptoms for people? So could we for other people who sneeze, provide a generalized framework whereby they can record their own symptoms, be it sneezing or other allergic reactions, and then gather external data and figure out some kind of relationship so someone is better informed as to what causes them to sneeze, be it a particular kind of hay fever from a grass or a tree pollen rather than just generalized hay fever, or a food allergy or various things. And at which point could we possibly reduce people's need for medication? That was like a really important end game. Can we reduce a person's reliance on using medication? So about 10 to 30% of the Western population is affected by allergic rhinitis. That's not what my wife has got. So allergic rhinitis, that's a traditional hay fever or say a cat allergy. And I'm going to extrapolate and wave my hands and say that's around 1.5 billion people around the world probably suffer from allergic rhinitis, and so probably more for rhinitis in general. And this is interesting and important because some antihistamines, it turns out, are now being linked to conditions like Alzheimer's. So it would be nice if we could help people take less of this medication to make their lives better and to give them a better chance of not getting weird complications later in life. So my wife sneezes a lot. This is a count of number of sneezes and number of days she has those many sneezes. It's rare that she sneezes 0 times in a day. It's quite likely she sneezes 1 time in a day. That's the number of days for one sneeze in a day. Quite likely she sneezes 2 times or 3 or 4, up to 10 times a day. So there are many days of the year in the last year's worth of recorded data where she sneezes that many times, up to 26 times in a day. And this is with and without antihistamine. For half the year, she's taking an antihistamine and half the year without. It's roughly day on, day off. So it's roughly it's a balanced data set in terms of antihistamine usage. So these sneeze counts are either with medication, which reduces the prevalence of sneezing, or without medication. So there's a lot of sneezes. So we formed a hypothesis. Ian's wife, Emily, suffers from non-allergic rhinitis. We say non-allergic. She was diagnosed by a doctor years ago with chronic persistent allergic rhinitis. So she sneezes because she comes into contact with some kind of allergen, like a cat or hay fever. However, she sneezes all year round, as you'll see. It's not seasonal. We've removed conditions like the cat, or even me, as some people have pointed out, because she's been traveling around the world. So she doesn't sneeze because of me, or because of the house, or because of our street, or because of our cat. She's had it for 20 years, and she's an advanced pattern recognition machine, like we all are, and she can't spot any obvious simple patterns. So it's not a trivial condition. It's probably a multi-factor condition, and it could well be both allergic, so hay fever, and non-allergic things like weather, for example. So we have some hypothesis. Possibly it's weather-related. That's a driver for some people with non-allergic rhinitis. Alcohol might make things worse. She self-reports that when she drinks beer in the evening, she's more likely to sneeze afterwards. So can we get data to support that? When we lived in Chile, the pollution was awful, and she had a bigger problem when we were living in Chile, so maybe pollution is a factor. So we need to get data to answer these questions. So here's how we gathered our data. As I mentioned, Emily is an iOS developer, so she wrote an app to do this. So she's written an app, it's open source on this GitHub account, so you can grab this and run this. She's got nice buttons where she just logs the symptoms, so we get sub-second accuracy with a GPS log as to where and when she has the symptom, be that a sneeze or watery eye, irritated nose, coughing, a whole bunch of symptoms, mainly sneezing or use of antihistamine. In the app, you can see what the logs look like, so the time, the location changes that iOS just records for you. Whenever you move location, it has a new stamp saying you've moved location. You were here, you're now over here.
Sorry, Ian.
Oh, go on.
We need a firm definition of sneeze. Does she let it out or does she keep it in?
Oh, she sneezes. Politely, but yeah, no, it's there is no attempt to suppress a sneeze. No, yeah, she sneezes. Yeah, she sneezes a lot. As you'll see, yeah. There's a good reason to try and solve this.
Where's the icon to say that you were in the room?
Oh, what, that I was in the room? No. So we don't record that I'm in the room or not, but we just know that when Emily is out of the country, she has the same prevalence of antihistamine usage and sneezes. So we've isolated me almost entirely. We don't know if it requires several wash cycles to take possible allergens out of clothing, which might still be on her clothing when she's traveling. We're pretty sure that's not the case, but there are some rough edges. So some data issues. Apple, being Apple, have a slightly different date-time format. It's got a different epoch date, so it's not the 1970s unique epoch, it's 2001 with a different day offset, which coincides with something to do with next step. And so we switched sensibly after discovering this to ISO 8601, so always recorded date times in ISO 8601. If you go underground, the phone confidently reports it has a location. It's at GPS 00, which is off the coast of Nigeria. So we have to do some fixes for that afterwards. In hindsight, there was a weak experimental design. Emily's recording positive incidences of a thing. So I have sneezed, I've taken alcohol. If she doesn't record sneezes, does it mean she didn't sneeze or she forgot to sneeze? Sneezes, she sneezes enough that we get enough data regardless of whether she misses one. But say with alcohol use, maybe we miss a critical factor. And so we think a day has no alcohol when there was one alcohol. So this positive data experimental design in hindsight is a bit weak, but it's hard to get beyond that and really start annotating someone's exact life. So just to remind you again, my wife sneezes a lot, from 1 time a day through to 26 times a day, and takes antihistamine every other day. Kind of a balanced data set for a classification task, you might consider. So this is data self-logged by Emily. This is a 1-year trace of data. This is the number of sneezes per day, so it's just a line chart bouncing up and down. You can see that rarely are there 0 sneezes per day. It's about roughly 1 every 8 days. Every other day has some number of sneezes per day, up to 26 in the middle of November. So I get a really good trace.
Is that not cold? Or is that like
So we now record colds, and it might well be the case that that was a cold, and then that will be the third condition of rhinitis, infectious rhinitis, when you sneeze because you've got a cold. So that could well be an outlier, absolutely. And we now, as part of our evolving experimental design, we now record whether there's a cold or medication for colds, like Sudafed, so we could isolate those kind of outliers.
What was happening in May? Was she on the cheek for a original?
Yes, good point. So May is because we have missing data. We have missing data because Emily performed a beta upgrade on her iOS code, and it helpfully deleted everything. Said, hey, you want to be a new iOS developer, so we're just going to trash your system. And we didn't want to warn you of that. You didn't want to check you had your backups. So it deleted everything. So after much scrabbling around, we realized we'd lost 5 days, but only 5 days, but still 5 days. That was very frustrating. And for both of us on a professional level, it was really quite embarrassing to lose 5 days of data early in the experiment, but nonetheless, it was annoying. So after that, we switched to using segment.io as an online backup as well. So all data is logged to segment.io as well as an offsite backup effectively. And this kind of barcodey thing down here, this is a bar if an antihistamine is taken, and it's white if there is no antihistamine taken. So you can see there are periods when there's compressed blue, there's lots of antihistamines being taken, and periods of white, and that's when there are no antihistamines being taken. So you get kind of this wave-like effect. You can see that there are times when there are more antihistamines and fewer antihistamines. And a quick breakdown on some of this data. So this is Monday through Sunday, so Monday, Tuesday, Wednesday, down to the weekend, and then hours of the day. Emily sneezes at 8 a.m. We wake up, Emily sits up, she sneezes, and that's just a morning thing. You can see this Monday through Friday, and then Saturday and Sunday, we wake up later, so she sneezes later, but she still sneezes. And then in the evening, she sneezes as well. At the beginning, we thought there was some kind of pattern in there, but as we've gained more data, it looks fairly consistent, and she sneezes less during the day. We don't know what drives that, but that's a pattern that's very consistent in the data. Sorry? So we changed the mattress. And when she's been traveling, she has, of course, changed flat or changed apartment, so for up to 3 weeks at a time, and the symptoms are the same. We did wonder if it was dust mites. Everyone has dust mites. They live in all of our clothing and beds and furniture. You can desiccate them by taking the apartment down to 50% humidity. We did that for 3 months. Symptoms didn't change, so don't think it's that. Antihistamine usage. So Emily wakes up, she sneezes. It's going to be a bad day, she thinks. She has an antihistamine in the morning. She tends not to have them during the day, or she has them in the evening if the symptoms have been really bad. This begs an interesting experimental question. Is the morning use of antihistamine because of yesterday's symptoms, or because of what she thinks is happening today? And if we're trying to do a prediction task, are we predicting today's morning's I've just woken up and feel grotty antihistamine usage? The end of the day, that's pretty clearly from the day's worth of exposure to stuff. But the morning one, we don't know. And we get different results depending on how we model that. So there's an open question there. If you've ever thought about this from your kind of work, I'd be interested in your feedback. Sneezes and antihistamine, there is a relationship between them. So medication, and we've resampled over 3 days. So if in 3 days, 3 antihistamines are taken, we're looking at the column with the 3 in it, and then the y-axis is the number of sneezes on those days. So on 3 days with no antihistamines in total, there are a few sneezes over those 3 days. On 3 days with 3 antihistamines, so an antihistamine every day, there are lots of sneezes, and the mean is higher. So the mean goes down, down, down. So it looks like there's a relationship between sneezes and medication. It turns out antihistamines reduce sneezing, they don't get rid of it. And so we see this positive relationship. And here I've used Seaborn, flipped it around, and we use number of sneezes in a linear regression to predict number of medications taken over 3 days. Here we just draw a line through it and it looks fine. Later on we validate this using cross-validation to check it is a true predictive relationship, and it is. This is just a nice diagram to show that there is a relationship. Some antihistamines work, but they don't work completely. One question Emily posed is, how long does an antihistamine last for? So can she time her usage of an antihistamine for best effect when she's got something coming up in the day? And potentially you might want to try antihistamine A like loratadine that she uses with something else. Giles, cetirizine, is that the right name for one of the other popular ones?
That's not popular.
So yeah, maybe she wants to use another one. It'll have a different half-life and a different effect and a different time to become effective and then become ineffective. So you could gather this kind of data to check the effectiveness of different medications. So here, if Emily took an antihistamine in the morning, so between 6 a.m. and 10 a.m., I mark that as a point in time, and then for the next 12 hours, I look at the number of sneezes per hour. So here we have 67 antihistamines, so 67 traces drawn in an really alpha shaded line. So it's 12 hours worth of 1, 2, 3, whatever, sneezes after an antihistamine. And if we sum all of these together, then we get this blue plot here. And what's interesting is, in the 0th hour of taking antihistamine, sneezes are high. On the 1st hour, sneezes are high. On the 2nd hour, sneezes are low. Turns out loratadine takes 2 hours to become fully dissolved into the body and to become effective. And then it's low for a number of hours, for about 9 hours afterwards. And then after that, potential for sneezing increases. And we see the number of sneezes going up again. So it's worn off after about 9 hours of being fairly effective. And if we simulate, that's the dashed line in the background, if we simulate the antihistamine dispersal in the body, it takes 2 hours to get fully dispersed, and it's got an 8-hour half-life, so every 8 hours it halves in strength, and then that's this simulated line here, and it drops off. So we get some idea as to, for Emily, on a very personal way, what level of antihistamine is effective and ineffective in her body. And that's going to vary by individual. So here we've got nice direct evidence. We can start calibrating dosages of loratadine if we want it on a personal level. Another question is, does alcohol increase the propensity to sneeze? John, is John in the room? John Sedder? Oh, John, there you are. So I've been chatting with various people about this, including John. I couldn't answer this to my satisfaction with my ability with stats. I was unhappy with the way I modelled things. I had a chat with John. He said, oh, well, that's a zero boosted Poisson distribution, and really you should be using PyMC3. I said, I don't know PyMC3. Aha, says John, you give me an excuse to play with your data. So I gave my data to John, and a few days ago he'd turned around the model. And so he gave me this model. I don't understand it yet. It occurred when I was organising the conference, so I haven't looked at it. But he tells me that he thinks we can say that whether an antihistamine is taken or not, if alcohol is used in the evening, the propensity for sneezes after the alcohol goes up. So it looks like sneezes are more likely if alcohol is taken. And you can shake your head, and I agree that I don't trust this data yet. One of the problems is bad data collection methodology. Emily used MyFitnessPal to record exactly the type of alcohol and the number she was taking, so a red wine and the number of them. Or she used the app to say, I had alcohol. She normally did it, but not always. So we didn't always get the right data. So we are now proposing a new experiment, 3 months of consistent data gathering, so we can answer this properly. Over to Giles. Let me... Oh, do you want to... Oh, how do I unplug this? Yeah. Right, there you go.
So learning relationships. So as Ian mentioned, conveniently our data set is split approximately 50-50, that Emily uses an antihistamine in half of the days in the data set. So it makes a very convenient target for a binary classification problem. We've observed seasonal trends in the data, as you would expect. You have temperature changes that are obvious throughout the year. There are lots of other seasonal trends. We want to look at environmental factors for the day and today's preceding the day that we're trying to predict, and not look at these, not to get too distracted by these seasonal trends. So we haven't done much in the way of time series analysis. We want an interpretable model. Simple is good, so if we can use logistic regression, we'll do that. We don't want to overcomplicate things. How do I get to the next slide?
Right. And then look over your shoulder.
Okay. We grab data from various sources. We use the R weather data package to get the daily weather data for London City Airport. Incidentally, this package now refuses to play, so a Python equivalent may be in the offing. So that gets us probably a couple of dozen columns of weather data, some of which may or may not be missing, but it's pretty useful stuff. We've also grabbed pollution data from the London Air website. That includes NOx, particulates, and again, it's a useful data set, but we would suggest caution. We've observed quite a variation between sampling from the different stations, and in particular there seems to be a lot of missing data, which we think is caused by broken sensors. Relationships with antihistamine usage there, well, we've got a 5-day moving average of the mean humidity on the left plot versus number of antihistamines taken over that 5-day period. It's quite difficult to eyeball these relationships, but sometimes we think we see something. And the scatter plot there, we can see that there may be some sort of relationship for that particular factor. We've run these graphs for everything, and we see these weak relationships, and we hope that that gives us some confidence that we can build a model around it. So feature augmentation, we've used pandas extensively to shift the data and create rolling means for varying numbers of days preceding the day where we're trying to predict if Emily is taking the antihistamine. We've got the alcohol consumption from Emily's app and also scraped from MyFitnessPal data, resampled to daily. Unfortunately, neither data source is complete, and MyFitnessPal is difficult to craft regex that are sensitive to actual alcohol consumption, because all the entries are the name of the product and not just a nice boolean of alcohol that's taken. Bus and underground usage data, Ian scraped from the online Oyster payments site. So I think, did you PDF it?
Mm-hmm.
And yeah, so it's PDF'd and then scraped. So that's very useful if, for instance, you want to know whether she's travelled on the Northern Line, which was one of the things we looked into because we thought it was pretty dirty and lots of particulates down there. So that lot together gave us a data frame with 84 features to work with and to really get stuck into with machine learning. So back to Ian.
All right, if I just get this start back on. And that sounds okay? Yep, perfect. So we have 84 features. There's about 20 raw data features that we're recording. And then we've created, as Giles was saying, lots of synthetic data off of that. So moving averages, standard deviations over time, directionality by change of moving average over time. So we've got 84 features, 330 rows. So this is a tiny data problem.
What's the average log per day?
The average,
Log, number of logs?
including movement changes, it's probably 50. But it really boils down to whether an antihistamine was taken, that's a log, and number of sneezes per day. Or are you talking about the weather data?
No, the number of sneezes.
Right, so yeah, so that's a very small number. It's just those raw events, and then the location changes. If Emily's going around a lot, there'll be a lot of those. But typically 30, 40 a day. So we're talking thousands of, or tens of thousands of events max in a year for one person. So we then built a variety of models: logistic regression, great, and random forests, and support vector machines with radial basis functions, because that's what everyone in medical does. And this was all going to be great, right? Only it turns out everything seemed to fall away. So we could build some complex models and get sort of 70, 80% predictive accuracy, allegedly, with lots of features. But the more I looked at them, I thought, these features are rubbish. This doesn't make any sense. We've got to be realistic here. We're making synthetic features, and it looks like there are just enough coincidental relationships between the synthetic feature and the actual signal we're trying to measure that something's coming through and is apparently predictive in the data we've got, but it's not going to hold up in the future. So that's rubbish. That's never going to work. I started peeling all of this back one step at a time, and then we kept on coming back to the fact that sneezes per day were predictive. This is under cross-validation, and whether the previous day an antihistamine was used. If it was used yesterday, it's less likely to be used today, and vice versa. And those are our best predictive features. So great, this doesn't explain anything. Really, really unhelpful. And what's wrong with the data? And then I got to thinking about, well, this data comes from London City Airport. So we've got external weather data and pollution data from around London. A lot of the day, Emily's in an air-conditioned office, so she's not subject to the external weather data. So in the summer, high summer, not so exposed to it, and in the winter, well, you're in heated buildings and heated homes, totally disconnected data set from what's observed on the runway at London City Airport. So that's a problem. So what if we look only at April to August, when Emily was not working for any particular client and she was consulting and travelling around London and working from home, and we live in a Victorian apartment with single glazed windows, so the internal temperature is fairly, and humidity and the like, is fairly representative of the outside weather that we're observing. Well, it turns out we get some predictive features, and this is kind of exciting. So, sneeze is a medication per day. So here we're looking at logistic regression, and we're looking at the coefficients inside them. And here I've summarized 5,000 independent models to see how stable the coefficients are. And that's why I'm using a box plot, and there's a couple of outliers shown. So we've got 5,000 models. All that matters really is that for a logistic regression model, we could assume that the most useful coefficient for any feature is the mean, say. So strong positive coefficient for sneezes. The more sneezes there are, the more likely an antihistamine is. For medication previous day, it's a negative coefficient. So if an antihistamine was taken yesterday, this being a negative coefficient, it's less likely a antihistamine will be taken today. For mean humidity 7 days, that's a 7-day moving average of the mean humidity of the outside world, negative relationship. So the higher the humidity, the damper it is, the less likely an antihistamine is. This is kind of interesting. Turns out that low humidity, dry air dries out your nasal lining, and that can give you a prevalence in the increase of sneezing. And sea level pressure reliably comes through, but I don't know why. I don't know what that means yet, and I'll get to that in a minute. So that was the model. This is a super simple model, but it seems to explain something. But do we trust it? Well, we don't know. I can form some hypotheses about how to proceed this year, and I hope the data supports the hypotheses. We don't know. We're not concluding anything at this stage. So, also, in the last year, we can look at weekends. Emily's not in the office at weekends. And it turns out if I rebuild the model for weekends only, actually the relationships seem to stand up. So we think we've got something, particularly with the humidity. So that's really quite exciting. So we want to see if that carries on this year. I mentioned that we're evolving our approach, so we're logging a better alcohol experiment more consistently now to try and get the right data for that. And at home, I've got loads of sensors, like, for example, a Blue Air home hygrometer. And this is dampness in the air, humidity, so recorded in the hygrometer, along with temperature and particulates. Separately, I've got a Giles 1100 Pro costing £400, which is an industrially calibrated particulate counter with a bit of a difficult interface, and a bunch of other sensors. So we're really trying to log the home environment to build a model up out of that. And we've used a portable hygrometer in Emily's office, and we know that it's roughly 40% humidity in the Mozilla office. And so we can start to interpolate another part of the day from that to add that to the modeling. And also move house. Well, actually, we're planning to move house this year. So if we move house, we get a totally different environment in a different bit of London, outside of North London and Kentish Town where the pollution is high, going down south of London where the pollution is much lower. Maybe we'll see some different behaviour there. That could be interesting. So next steps. We're getting our second year of data. This is really exciting. And we've invited a couple of people to join the trial. So we've got several other people logging their data with different symptoms and different drivers, but all around allergic and non-allergic rhinitis. So we're going to get different sets of data. And if you suffer from this, or someone you know suffers from this, and you're interested in joining the trial, then I'd love to have a chat about this as well. We want a few more people. I kind of want 10 or so for this next year, so we can stay on top of it. We're keeping the data private, we're not publishing it, so Emily's allowed me to talk about this, but we're not giving the data away. I don't want to give away GPS traces of everyone's life. That would be a really bad thing, even though Google and Apple have all of this, of course, but I don't want to be just uploading it to the internet. So if you're interested in that, come and have a chat with me. One thing we can do is regress, rather than classify true or false antihistamine usage for a day. What if we turn it into a 3-day resample, where we count the number of antihistamines over several days, and we incorporate several days worth of humidity into, say, a mean or something else, and then we regress on a 3-day challenge, so we look at the problem very differently. I've got a question for you, for anyone who's particularly strong with your underlying stats and logistic regression. Logistic regression assumes independent and identically distributed data, and we're using a time series that we've randomly shuffled, but today's weather is, you're nodding, shaking, nodding. Can we chat afterwards? All right. So we know that our data is not independent and identically distributed. Yesterday's weather is the best predictor of today's weather unless you've got a very complex model. So there are strong relationships there. Pragmatically, this works. Cross-validation says this is good, but we're busting some of the underlying assumptions. So if anyone's thought hard about this, I've tried to think about it, I don't know. If you've got feedback, I'd love to hear it. And another thing is we're testing on randomized days, so we've shuffled the days and then we do cross-validation, and instead one thing we could do is just take time as a series, train on say 2 months, and then test a week ahead, slide forward a week, test on 2 months, test on a week afterwards. So there are other ways we can test the data, but I'm pretty sure from previous experiments this is going to hold up. And we've also been introduced to some very strong academic research groups now, so now we can get some academics who really know this problem to come and help us to interpret the model, propose new experiments, and propose new ways of gathering data. And obviously a final potential is to strap not just sensors to the house, but also to the wife. Very exciting. She's less excited by that possibility, but it turns out there are devices like the Atmo tube. It's a small Bluetooth device. You put it onto your bag, it reports via Bluetooth pollution in real time and other environmental data that you're carrying on your backpack. So this will give us a much higher fidelity model of my wife's environment, sort of 5 meters squared around her. That could be really interesting. So that's where we are with that. Right. It's a challenging problem. We thought we would find some stronger relationships more readily. Instead, after 3, 4, 5, 6 months worth of much hand wringing and shouting at the sky, we found one signal that we trust. That's great, we found a signal, hooray! But I want to find more than one, so we've got to do more work. We think we can answer, or no, we can answer how effective is an antihistamine, loratadine in this case, for my wife's case. We can't yet answer, does alcohol make sneezing more likely? And we find no evidence yet that air pollution in London, PM2.5, PM10 and NO2, has any relationship with the prevalence of her use of antihistamines. I think we will find it, but it might be a much subtler thing, and that's where the academic collaboration comes in. I think we're basically there. These are all the tools that we've used. Python 3, obviously. And a big shout out to Anaconda and Pandas, R for preparing the data, and scikit-learn, SQLite from the data on the device, and then HDF, local storage of the data. Is that us? That's us. Thank you very much. And whoever's on the room timing, how long do we have?
You have about 9 minutes. You timed it like a Swiss watch.
Oh, blimey. Go us. Right, okay. Any questions in that case? We've got a few minutes. Tim?
The one thing, you were talking about the humidity, so high humidity is protective.
Yes.
Yeah, but then you also said that dust mites could be harmful.
I'm pretty sure we've ruled that out. It is a condition for some people, I know.
I just think you said the way you tackled dust mites was by reducing the humidity
Yes.
a lot. So is it not?
Oh, right.
It's dust mites. You either get the dust mites
Right,
or you get
so yeah, one of the things we did was use the hygrometer, use this one here. At one point in the winter, this is November, it was raining a lot, we were drying our washing inside, it got very damp in the house, so we dried the house out thoroughly, and we kept it at 50% to dry out those pesky dust mites that might have been having a happy environment for the few weeks that we let it get damp. And then we read about the dust mites, oh, this is rubbish. So it's great that we're getting rid of those, maybe, and if they are a problem, but also we're drying out the air, which might be a problem for Emily. So we don't know. And I'm trying not to modify the environment too much. I'm trying to get clean data for this stage. Another question. You, sir.
I noticed that in the beginning of the day, at the end of the day, sneezes much more than the middle of the day. Have you tested, I don't know if your wife uses sleep in the middle of the day.
No. I haven't tried putting her to sleep either.
I think that would be interesting if the sneezes increase before and after the sleep in the
Right,
middle of the day.
yep.
Then maybe
Some people have noted that it might be either the body relaxing and you're prone, and then by sitting up you change the blood flow and you change the airflow, and if a desensitized nasal tissue is suddenly sensitized again, it could be that. It could just be the increase in the volume of air going through, because when you wake up you breathe more air. And this is again why I'm keen to collaborate with the academics, because they should know the answers to these questions, and they should have seen this in other people, and they may have insight. Whereas we're just making this up as we go along.
If you're trying to assess the effectiveness of antihistamines, shouldn't that be an independent variable? Shouldn't you randomly take antihistamines?
Yes, I'm not allowed to. I cannot forbid my wife from trying to feel less rubbish when things are bad.
That could be problematic, right?
Yeah, totally. Yeah. Oh no, the confounders all over the place here. Yeah, no, this is not a clean, wonderful setting. I have not suggested to my wife that I put her into an isolated chamber for a year and see how she reacts to things. It's not going to work. And this is, I think, an interesting thing. There's a number of things that we can't easily control for in our environment, and yet we have to live our life. If you suffer from a bad complaint, maybe not a terminal one, but maybe something that makes your life a bit worse than it otherwise could be, why couldn't we use these supercomputers in our pocket and the sensors that are now becoming very cheap to monitor our life and to improve things, at which point we have to deal with the confounders. And so here, part of the reason for this is to try to get a handle on this, because this is only going to become more important in the future. I think there's going to be an awful lot of work to be done here in the future. And I figure trying to make people's lives better is a good thing, and you can't strap them into an isolated environment, so you just got to deal with it.
Have you thought about placebos?
No, again, yep, a tablet, yep, sure. No. Have run various experiments on my wife. Only given her migraines on a couple of occasions, and she's still open to it. I don't know if she'd like the idea of placebos, but I like your thinking.
Yeah, stress is clearly important, considered an important factor, and it's clearly hard to measure. But I just talked to some friend recently who has a problem carpal tunnel,
Yep.
and he's logging the number of keystrokes.
Okay.
And the fact that she's a programmer is like
Yeah.
you can measure how much she's working and.
Right. Yeah, and we've discussed this. There's an exercise log via MyFitnessPal that we haven't tapped into yet, because exercise is a stressor. And then there's all the other stresses of everyday life, and we haven't even thought about how to log that. And partly that's, again, with the academics, we can propose that as a hypothesis, and if they say, actually, that could be totally key, great, we should do something about it. We're cautious about logging too many things, because there's just too much stuff. We could log everything, and we could then maybe even find signals that are coincidental or true signals, but all these things are harder to log, and so we have to be pragmatic with our time. But I agree, we need to at least consider it. Yeah, totally, right. So, absolutely, we could record that as well, yeah.
So I'm just wondering about the part that you mentioned, where you got some sort of 70 or 80% accuracy that you mentioned, but you didn't trust the features.
Well, yeah, I'm not going to conclude on those results just yet, but I'm happy enough to stand up here and say, I think it's all right.
No, but before that, you mentioned that you got results and some features were kind of rubbish, so
I can bust out one of my appendix slides. So here's where I wrote a custom recursive feature elimination method, which exhaustively tried all features, all 84 features, took out the least useful one, and then we get a new score, and then try all of them together, so 83 features at a time, on 50 repeats of 5-fold cross-validation, taking the average, and then take it, so there's even high variance even just doing that, but increasingly taking out all of the features, and then you end up getting an increasingly good score, and things are looking really good, and then you pull out the last couple and it drops off to nothing, and that's fine, and it turns out the last couple of things that you pull out, it's just sneezes today and antihistamines yesterday, so they're the most consistent features, and all the rest of these are just... Yeah, sure. I mean, I got rid of all of these, and I get this, and I go, well, look, for the year, I've got nearly 70% accuracy. But when I look at it, it's the 5-day standard deviation change of the 2-day thing. I think, this is garbage. This is a feature that's coincidental rather than a predictive feature. And I believe if we got more data outside of the cross-validation period, that relationship would drop away. So I just don't trust it.
Cool.
A couple of questions. The first one is, why don't you also add a wearable device so that you also have blood pressure and hours of sleep?
You don't get blood pressure from a wearable device easily. You still need a large mercury band, right? And there is a limit to the Borgification of my wife that I can do at the moment. So I would like more data, right? And it won't be long before we have either simple external devices or internal devices. It won't be long, 5-10 years, say. But we can see this is coming. People who have diabetes have internal devices to report their condition, insulin levels, to a device for the automatic release of medication, right? There's a closed feedback loop that you can embed inside yourself to look after yourself, so you haven't got to rely upon yourself to get it right. So this is all coming, and this is all sort of 5 years ago or 5 years in the future. So we want more. Yeah, I want more of this, but right now I'm limited to how many things I can get my wife to reliably do without getting really annoyed with me.
Another question. I also
We've got to wrap up
All right.
very shortly.
Okay. So quick question, then we'll wrap up.
Yeah, I assume that there have been times when she wanted to take a medication, but
Yep.
she didn't have that available. Have you also measured that?
No, we haven't. That's a good question, but she almost always has her medication. Because it's a tiny tablet, right? They're easy to carry, so she almost always has them. All right. Thank you very much, everyone.